Welcome back. In the previous class I was talking about the new notion of stability, that is called arbitrary time stability, and what was our main goal, how to control the time of convergence, and what was our objective. We want that time of convergence is independent of the initial condition as well as the system parameter. Now in this lecture I am going to extend that kind of concept to design terminal sliding mode control. So we have already seen that in terminal sliding mode control, same like the classical sliding mode control, we have two phases. One is actually reaching phase and another is sliding phase, and both phase actually occur in finite time, and due to that reason overall convergence is actually occur in finite time, but time of convergence is actually sensitive to the initial time as well as the parameter. Now in this lecture we are trying to control the time of convergence from the point where trajectory is going to hit to the sliding surface to the origin. Okay, so during sliding mode we are trying to control the time of convergence, and it is possible to show that in this way somehow overall time we can able to make that is independent of the initial condition as well as the parameter. So objective of lecture to present arbitrary time terminal sliding mode control, and we have already seen the motivation, because I want to design again some kind of sliding surface such that we can reach here in finite time, and after that in finite time I can able to move from here to here. And we have already seen that classical terminal sliding mode control is somehow suffered from the singularity, and due to that reason non-singular sliding mode control comes into picture. But concept of non-singular sliding mode control is only limited up to second order. So it is possible to show that using this particular methodology we can able to achieve exactly same kind of objective, and we can able to extend the design up to any order, and singularity problem also one can able to solve. Okay, this work is actually done in the collaboration with the Professor Jing Yu and Professor Vigyan Bandyopadhyay along with my student Anil Pal. So basically we are trying to analyze the sliding phase control. So what is our main objective? Suppose that if I have some kind of initial condition and from here to here I will reach in some kind of time TR. So this is reaching time. This time is actually function of the initial condition as well as the parameter. But from here to here whatever time we are going to select, so that is independent of the initial condition, and due to that reason overall time from here to here it is possible to show that somehow become independent of parameter as well as initial condition, because this phase I can able to make as quick as possible. Just one thing that we have to make sure that whatever time of convergence I am going to select, that is greater than TR, and after that we are also going to show you another algorithm. Using that it is possible to show that even if this reaching time is unknown, then how to actually retune the algorithm such that one can able to achieve this particular objective. And stability analysis I am going to perform based on the Lyapunov function which we have discussed in the previous lecture, and we are going to get some kind of form for nth order integrator chain of integrator system. So obviously what is comparative benefit? So I have already explained that this methodology somehow solve the one of the very important classical problem that is associated with the terminal sliding mode control, that is singularity problem. Okay, overall time of convergence it is possible to show that is independent of initial condition as well as the parameter. Okay, and we are also trying to show that there is some kind of explicit controller, sliding mode kind of controller, and that controller is also insensitive with respect to matched uncertainty, and we are also going to give the higher order extension of this, means beyond second order. So, let us start with the system dynamics. So, this will represent some kind of nonlinear system. In this particular nonlinear system, this var theta, this is called var theta, that is actually design parameter or some kind of system parameter, you can tell. Now, xt0 is the initial condition, and I am assuming that x belongs to Rn, means n number of state variable I have. Without loss of generality, I am assuming that x equal to 0 is my equilibrium point. And obviously then this kind of notion we have already discussed in the previous class, that is fixed time stability. So, this definition I have taken from Polyakov work. So, x equal to 0, that is globally finite time stable. It means that if I start anywhere from the state space, our trajectory remains bounded, and after that we will converge in some kind of time which is upper bounded by some maximum time t max. Okay. So, this is nothing but the settling time, that is function of the initial time as well as the x0. It is possible to show that this is also function of this parameter, that is var theta. Okay. Now, with help of previous definition, we are going to actually define new definition, and this is actually copied from our previous paper. So, first paper in arbitrary sliding mode control. So, this time of convergence Ta, that is independent of any system parameter also. Okay. So, basically this is independent of initial condition. Why? Because we are talking about fixed time stability, and obviously whenever we will impose this kind of condition, then this is independent of parameter also. And if Ta is greater than Tes, basically we are somehow some kind of time that is coming from the system. If Ta, our time, selected time is greater than this, then we are telling that this is weak arbitrary time stable, and Ts, that is a strong arbitrary time stable. And obviously if Ta is not tuned based on the parameter, then we are talking that kind of stability as a free will stability. Okay. So, free will term I am not going to actually explicitly use here, because now since obviously Ta is independent of nu, so some kind of arbitrary time stability comes into picture. So, either you can interpret that as a free will, so that is just a terminology. Particularly for control engineer, control is very important, and objective is important. So, objective is to control the total time of convergence, and Ts is the exact settling time. So, obviously free will arbitrary time stability is a stronger notion than the prescribed time. In prescribed time, basically again time of convergence, whatever here time of convergence, we are trying to go to close of this time of convergence. Okay. And that is only applicable to up to T max if you see the definition of prescribed time stability, but this definition whatever we are telling, that is extended up to t equal to infinity. Okay. It means that I can able to converge to equilibrium point, and after that I am also going to maintain and fixed time stability and finite time stability, and in this way this is very strong notion. And Lyapunov characterization we have already seen that if this Lyapunov function is bounded by two k class function, so beta 1 and beta 2 is class k function, and after that v dot equal to 0 for all t greater than equal to Tf. Before that they are going to satisfy some kind of expression, and this particular equality if you see, then we have already seen in previous class that this is actually arbitrary time stable, where Tf is nothing but T0 plus Ta, time of convergence. So we want to maintain time of convergence Ta, so that is defined like this. Okay. So in this way basically this is differential inequality, and after that if I will apply the comparison principle, then it is possible to show that within this particular time, if I start our system at T0, then finally we will converge to the 0, and after that due to this condition, since v equal to 0 already from this particular design and v dot equal to 0. So if you apply Newton's first law, then we are going to maintain here. Now one of the structure we have suggested in the previous class, if I have first order integrator, then it is possible to show that if you design this v1 like this, then within time time Tf, and Tf I have already told you that Tf is nothing but T0 plus Ta. Okay, so if you maintain T equal to 0, then basically Tf equal to Ta. So without loss of generality, in this whole lecture I am going to talk about the convergence time is Tf. What does it mean? That I am going to start this system at T0 equal to 0, and now using Lyapunov function again I will get this kind of inequality, and one can able to show that x1 equal to 0 is actually arbitrary time stable. Now one can able to extend this result for second order integrator system also. How to extend? One can able to apply the back stepping control. Okay, so what you can do, you can design some kind of change of the coordinate, and what is beauty of this coordinate? I am assuming that x1 dot equal to minus phi 1, and phi 1 basically we are going to design like this. Okay, so if you are going to design phi 1 like this, then it is possible to show that x1 equal to 0 in predefined time, and that predefined time Tf you can able to easily select. Okay, so if you start from T equal to 0, then Tf within that Tf time x1 equal to 0. Okay, now one more important point I have already discussed in the previous lecture. This is actually locally Lifshitz in x1 and piecewise continuous in T up to Tf if you just exclude Tf. Okay, so somehow discontinuity is going to lie on time. Okay, so since discontinuity is not lying on x1 state, and due to that reason you can able to take differentiation up to means open bracket up to Tf. Okay, and due to that reason I can able to take derivative of this. That is the reason. Okay, obviously some kind of control if you design phi 1 like x1 power half signum x1 something like this with some gain k1, obviously this is not differentiable at x1 equal to 0. Why? Because discontinuity is going to lie on x1 equal to 0. But what is beauty of this? Discontinuity is only lie in time. Okay, and due to that reason differential process is possible, and one can able to apply the back stepping method. Okay, now what I am going to do here, x2 I am going to substitute, so g2 minus phi 1 comes into picture, and after that I am going to define g2 dot. So g2 dot is nothing but x2 dot, so here v2 comes into picture and phi dot comes into picture. So phi dot is differentiable, and it is also possible to show that is bounded, and due to that reason now I can able to design the control action with the help of Lyapunov function. So this is actually totally inspired from the back stepping design. So in back stepping design, first I will stabilize first order system, and after that we will move for the overall second order system by taking the coordinate change. So same principle I have applied here, and you can see that if I again select phi 2, because I have to stabilize g2, so I have to select phi 2, that is nothing but the after cancellation of all other term, that phi 2 basically comes into picture. So phi 2 structure should looks like this. Okay, and if I will do this, so by Lyapunov stability you can see that I have this kind of term. Okay, so v dot is either governed by this term or this term, so depending on their value. So in that particular way, since v is given like this, so v is either max of mod x1 or g2, and in this way if I will substitute, I will again return back to the exactly same equation. In next slide you can see that if I define rho variable as a rho, then exactly I will get same kind of differential inequality like the arbitrary time stability, and due to that reason rho equal to 0 in arbitrary time, that is Tf, and if rho equal to 0, then v is also 0 or tending towards 0 in Tf. Okay, and now we are going to maintain v dot equal to 0 next subsequent interval, and due to that reason it is possible to show that one can able to converge in this particular time. So both variable is going to converge to 0 in that particular time. So in that way I can able to stabilize x1 and x2 within Tf time. Now another important thing, I have to maintain that. So how to maintain? So after once you will get x1 equal to 0 and x2 equal to 0, so just switch your dynamic to 0 0. Okay, and due to that reason in this type of control switching is very important. Now I am going to talk about how to extend this kind of idea whatever we have previously discussed to any order system, arbitrary order system, and here you can see that I have some kind of disturbance that is going to enter through the control channel. So this is meshed uncertainty, and we are using assuming that this is bonded. So for all supremum T, this is actually bonded by D0. So what is our objective? Now our objective to design free will arbitrary time convergent. Free will means time of convergence I can select independent of the system parameter as well as the initial time, and due to that reason this word is actually come into picture. So I have taken two cases. Suppose that if I have known reaching time TR and unknown reaching time TR. Okay, so most of time what happens that whenever I have practical system, so practical system is lying in compact set. So by doing worst case analysis, it is possible to show that one can able to estimate time of convergence to the sliding surface. So always there is some kind of TR information is there, and it is possible to show that if you are going to keep TF, total time of convergence, greater than TR, then always you can able to move within that TF. Okay, so the only requirement is TF should be greater than equal to TR, but most of time in practical situation this is unknown, and due to that reason you have to slowly tune TF, because TF I have to maintain TR. So we have to provide some kind of algorithm such that controller will always check that TF is greater than TR or not, and if that is not the case, they will improve their time. So now I am going to start with this system. What I am going to assume here, that whatever UN that is actually bonded, it is possible to show that is bonded. Okay, we have already shown in the literature that UN is bonded. Okay, now what I am going to do, that I am going to first design when we are assuming TR is known. Okay, if TR is known, then what is benefit, that TF easily I can able to tune without applying any algorithm. And second design, obviously I am going to assume that TR is unknown. Okay, so here obviously in classical or conventional sliding mode control that is coined by Professor Utkin or Emelianov, where we are what basically we are doing, we are reaching from any initial point to here in finite time, and after that asymptotically we are maintaining to the equilibrium point. Here we are trying to maintain this phase arbitrary, that is our main goal. Okay, this phase we are not going to change. Okay, now key assumption here that TF is greater than TR, but it is possible that we have in next lecture I will give you some kind of algorithm where you are also able to control this time of convergence. So in arbitrary way you can able to converge from here to here. So this time also you can able to control, but I think that is not required. Okay, and due to that reason this design step is also good enough for the implementation purpose. Now what is our main theorem? So main theorem is finite time reaching phase dynamics we have, and after that free will weak arbitrary time stable sliding phase we have. Actually why we are telling weak, because most of time whatever TA we are selecting, so our trajectory will go to very close to TA, but most of time that is not exact. Okay, and due to that reason weak kind of stability at least we expect, and after that now you can see that within this time our control is given like this, and after T equal to TF again that will switch to the classical sliding mode control, because uncertainty is always present, and due to that reason you have to always activate your control. So once you are at equilibrium point, now another aim to how to maintain this equilibrium point, and due to that reason you have to switch to some kind of robust control. So any robust control is okay, but I have to maintain insensitivity with in presence of any time varying uncertainty also, and due to that reason it is better to switch to some kind of classical sliding mode or higher order sliding mode control algorithm. You can see that here again control is 0, because x2 xn up to everything is 0, and what is role of this signum Sn, that is actually going to switch with very high switching frequency such that you can able to maintain here. Okay, so here basically whenever we are selecting gain, so based on Hurwitz parameter I am going to select the gain, because somehow after once I am at equilibrium point I have to maintain here. So this is nothing but some kind of sliding mode control designed for nth order system with DT. Okay, so classical sliding mode I am going to switch. Okay, so basically our contribution here, that before that how to reach in this given time TF if T0 equal to 0. Okay, and obviously if T0 is Ta, at that time Tf is nothing but T0 plus Ta, so time of convergence is Ta. Okay. So now before Tf I have this kind of dynamics omega, and we are going to select based on the arbitrary time sliding mode arbitrary time convergence principle. Okay, and after that Tf I have basically classical sliding surface. Okay, so here I am going to switch the sliding mode control as well as sliding surface also I am going to switch. Okay, so two different switching is actually involved here. So let us try to see for the second order system. So if I have second order system, so what is first step? First step, using back stepping, okay, you can try to design the first control omega 1, because if you have second order system, then obviously during sliding phase you can see that system dynamics is nothing but s equal to 0, and after that I have dynamics is given by x dot and whatever reduced order dynamics that comes into picture, and due to that reason first order arbitrary time sliding mode is only enough. Okay, now what I am going to do, I am going to design this S2 sliding surface, that is x2 plus omega 1. Why we are selecting like this? Because if omega 1 is equal to minus V1, and what is V1? From here easily you can able to see that whenever I have first order system, so I have already designed, so same terminology I am going to consistent here. So if I have V1 and x1 dot equal to V1, where this is negative, so I can able to show that V1 tending towards 0 as t tending towards some time Tf if initial time is 0. Okay, and due to that reason same kind of control I am going to maintain here, and somehow this control is act once we are in sliding. Okay, so at that time S2 equal to 0 and x2 is exactly replaced by the minus V1. Okay, now what is our goal? Our goal to converge to this sliding surface. So for that I am going to design based on the classical sliding mode principle, that I will select disturbance that is greater than d0. Okay, and after that I have finally, if you see, if you apply this kind of control, then our overall dynamics, sliding dynamics is x2 equal to minus k signum x2 plus dt. So in this way I can able to show x2 equal to 0 in finite time. Okay, and that finite time is depending on the initial time as well as initial parameter. Now if our Tf final time is greater than Tr, so somehow you can see that here Tf minus Tr comes into picture. Okay, because T is somehow giving the time, every time this is updating. So Tr, so this will convert x2 become 0 between Tf minus Tr, that much of time that will become 0. Okay, so if this time is short, so obviously what happens, this variable omega and omega dot may be larger, and due to that reason this time you have to select sufficiently large. Okay, most of time in practical system one can able to easily do it. So once S2 equal to this, after what happens, before time t greater than equal less than equal to Tf, I have to apply or I have to design sliding surface based on arbitrary time principle. But once I will achieve the goal, then I have to actually shift to the classical sliding mode control, because as we move towards the equilibrium point, you can see that this term is actually tending towards 0. Obviously this is also tending towards 0, and 0 by 0 form comes into picture, and what is beauty, this 0 and 0 by form always give you the finite value. Okay, and due to that reason this control is always finite. Okay, now ut I am going to shift to the classical sliding mode control. So I hope that you are already well aware that if I have some kind of system u plus dt, then how to design sliding mode control, you can define the sliding surface like this, and after that you can take the derivative of this. So that is nothing but k1 and x1 dot equal to x2 and x2 dot equal to u plus dt, and now you can design u. So u, if you design, that is equal to minus k1 x1 and minus k2 signum x2. So obviously what happens, that this term will cancel out, and after that I have this kind of dynamics. So within finite time it is possible to show at S2 equal to 0. So and already we are at 0. Okay, so if some kind of mismatch also, classical sliding mode is going to take care about this. Okay, so this kind of behavior we are analyzing when t is greater than equal to Tf. Now similarly you can able to extend exactly same idea for the third order system, but in third order system obviously reduced order dynamics, if you see carefully, then that is represented by second order, and at that time you need second order arbitrary time stability concept. Okay, so you have to go through the back stepping. So using back stepping, now I can able to design select x3 such that x1 and x2 will become stable in arbitrary time, and we have already seen during the back stepping that how to design that kind of control. Okay, once I will done that job, again next job to maintain the whatever transform variable S3 that equal to 0 in finite time. So for that, if I select control like this, so it is possible to show that S3 equal to 0, and once S3 equal to 0, then you can see here that S3 equal to 0, then X3 equal to minus omega 2, and what is omega 2? Omega 2 is V2, and by back stepping it is possible to show that X1 and X2 both equal to 0 in arbitrary time, and if X1 and X2 equal to 0 and X3 is already 0, so there is no other choice, X3 also equal to 0 in arbitrary time. In this way you can able to extend this kind of concept for any order. Okay, so every time you have to perform the back stepping. Based on back stepping, you can select sliding mode control based on the last step, and after that if you employ the control and using the Lyapunov way, it is possible to show that you can able to get arbitrary time stability. So using induction, one can easily able to show that this kind of inequality comes into picture, and finally we will get this kind of last inequality such that all rho plus r equal to 0 in finite time. So whenever you are applying induction, so you have to check for n equal to 1. So for n equal to 1, that is arbitrary time stability. So by induction it is possible to show mathematical induction that for this result is true for all n belongs to n. In this way one can able to extend the proof for any order. Okay. Now you have to become little more careful whenever you are selecting the parameter. Okay, so parameter selection should satisfy this kind of condition in order to maintain the Lyapunov stability. Okay, so it means that eta I, if you have first order system, then that is greater than 1, but if you have second order system, then that is greater than 2, if third order system, then that is greater than 3. Okay, so this kind of things you have to take care whenever you are designing. So if you have nth order system, then ni, whatever gain you are going to select, so all gains should be greater than the n. So that kind of things you have to take care, and obviously here that control design involve the conventional sliding mode control. So chattering must present. So one can able to again minimize the chattering by designing first phase reaching phase using the super twisting algorithm. Okay, so at that time in place of discontinuous control, you can involve this kind of control signum s and plus x2, and here x2 dot some fictitious variable. So x2 tilde dot equal to minus k2 signum s. In that particular way also you can able to minimize the chattering. So chattering minimization is always possible. Okay, so this kind of sliding mode control is called free will arbitrary time sliding mode control, because time of convergence you can able to select. Obviously every system has some own dynamics, so whatever time of convergence you are going to select, okay, so based on that you have to select the time of convergence. Time of convergence will never close to 0. Okay, some finite value that will come, because every system takes some time to respond the control action. Okay, and obviously this will handle some kind of uncertainty, because I am involving the sliding mode control, and main intention of sliding mode control to actually compensate the meshed uncertainty. Okay, now suppose that if TF, so I have to realize TF, but TR, that reaching time, it means that suppose that this time TR is not known to us. Okay, so for that I have to actually write this kind of algorithm. So TF I can arbitrary, initially I can select some value, and after that I will check that s equal to 0 or not, sliding surface equal to 0 or not. Okay, so now if s equal to 0, so whatever current value I have selected, that is okay. Now I will go to the third step, and after that repeat the second step. So I will wait that by improving this time, I will wait that when s equal to 0. If TF is greater than TC, then TF is realizable, and if not, then you have to select new TF. So in this way, particularly always I can modify slowly the TF and I will reach here, and after that I can able to maintain the equilibrium point within some kind of arbitrary time. Okay. So now what I have done, I have taken second order system with this kind of uncertainty, meshed uncertainty. We have selected the time of convergence, that is 15 second and 20 second, and here gains I have selected like this. Okay. And after that, what is our observation, that state stabilize within TF time. Control, obviously actually chattering comes into picture because discontinuous control, classical sliding mode control I have to apply and I am applying. But if I will switch to the super twisting based control, then obviously this will minimize. Okay. And large control at TF due to the forced convergence, because what happens that sometime, suppose that if you are selecting TF equal to 5 second and this convergence will take within 4.5 seconds. So you have just 0.5 second to move from here to here. Okay. And due to that reason, 0.5 second your control should be large enough to handle this. Okay, from convergence from here to here, and due to that reason some kind of variation you can able to feel whenever we are converging from here to here, because this control is actually responsible for arbitrary time convergence from here to here. So that kind of things you can also able to see from the simulation. Okay. But whenever you are implementing control, so control implementation, first we are doing several trial, then we are implementing, and due to that reason you can easily able to select the time of convergence. So this kind of phenomena comes into picture if your time of convergence is TF is not very large than TR. Okay. And obviously you can able to see that control is not so high, means that is actually less than 20, and similar kind of things we have here. Okay. So this phenomena is basically occur because we don't know that how much time I have to converge from here to here, but I have to make it arbitrary. Okay. So if this time is short, then denominator of the control, so you can see any control, then easily you can able to understand this TF minus TR. So this will very high. Okay. And due to that reason this kind of action basically comes into picture. Similarly, you can able to do analysis for third order system, and it is possible to show now in case of third order system, control is actually here chattering is occur because we are implementing the sum of on off control. But here if time of convergence I have selected, that is sufficient enough, you can see that that kind of a spike will not come. Okay. So now it is time to conclude this lecture. So what we have seen? We have seen that one of the classical problem of the singular terminal sliding mode control is that you cannot able to start from anywhere, because we feel we will actually occur some kind of singularity if you start anywhere in the state space, and due to that reason non-singular terminal sliding mode comes into picture. But this is another solution to avoid the singularity of terminal sliding mode control. You can use the concept of arbitrary sliding mode control. One more thing I am going to give you the hint, that since in next class I am going to show you that from here to here also one can able to reach in arbitrary time. Okay. And due to that reason you can easily able to now control from here to here in arbitrary time and here to here in arbitrary time. Okay. So that problem, whatever problem of time of convergence, you can easily able to solve by using the help of the next lecture. Okay. But most of time what we feel that time of convergence for the practical system is sufficiently large, and due to that reason means this kind of problem will not come into picture. Okay. Particularly those system which is little bit slow, particularly for the mechanical system, and we have demonstrated the stabilization for nth order Pattern chain of integrator, and after that we have done the comprehensive simulation both for second order and third order system, and adaptive algorithm we have also proposed whenever TR is not known in advance. So with this particular remark I am going to end this lecture. Thank you very much.